Hello everyone, this is Sushma. In this video, I will share how I use the diagnostic plots to understand about the usefulness of my linear regression model. A famous quote by Dr. George Box states that all models are wrong, but some are useful. Indeed, every statistical model is an approximation of reality. So, in my work, I do not aim for a perfectly fitting model. Instead, I focus on whether my model is useful as long as the model specification is reasonable. So, one of the main ways to avoid a serious specification error is by doing a thorough review of existing theory and literature around the research question. For example, if we are studying the association of physical exercise and blood pressure, failing to adjust for the effect of confounding variables such as age, gender, or race could lead to a misspecified model. So once we do that, based on the conceptual framework that we derive from the literature review, we can then specify our empirical model. And then the next step is using our data to estimate the model. But by keeping in mind that your data needs to satisfy certain assumptions underlying the model for the inference to be valid and reliable. So the four main assumptions for a linear model include linearity, independence, normality, and homoskedasticity, also called equal variance. So the LION acronym can help you remember them. So in the next section, let's look at the diagnostic plots from a linear regression model in R to check what the diagnostic plot will tell us about this assumption. So in my R window here, you can see that I have loaded a simulated data as data here. And okay, I haven't. So let me run it. And here you can see that there are two variables in the data set, x and y. Here, x is the independent variable and y is the dependent variable, and both of them are numeric. To look into the more summary measures of these variables of interest, such as mean and median, I'm using here the describe function. And here on the R console, we can see the different summary measures here for these two variables, x and y. Here I'm quickly running a histogram plot for the outcome variable y using GM histogram and ggplot, and I also let the I also plotted a normal distribution curve here overlaid in this histogram. And here we can see a normally distributed bell-shaped looking curve here that indicates that the variable y is normally distributed. Now let's run the linear regression model using LM function here. I have saved the model fit results as model fit, and let me run it, and then we can see the summary of the model fit results. Here in the R console, we can see a lot of information and results here. The parameter estimates and standard error, p-values, and others. So let's not go into those results for the purpose of this video because we are more interested in the model fit diagnostic plots. So let's get those plots using the plot function. So here I ran this line here, and in the R console it shows hit return to see next plot. So I hit enter here, and then on the right in the plot section we can see a residuals versus fitted plot, and then I hit enter again, and there we can see a normal QQ plot. Hit enter, scale location plot, and hit enter, and there is a residual versus leverage plot. So let's keep all of these plots together using par EMF row 2x2 layout. Let me run this line here, and then plot model fit. Doing that, it gives all of these 4 plots together. Now let's recall those 4 assumptions that we discussed earlier in the acronym LINE. So the first is the linearity, L for linearity, and according to the linearity assumption, the mean of y given x are a linear function of x. In another word, the means of each of the y given x distributions may be joined by a straight line. So to check this assumption in the diagnostic plot, we look into this first plot, residual versus fitted values plot, which is basically for the linearity assumption to hold. In this plot, the residuals should be randomly distributed around this dashed horizontal line without any distinct patterns. That means if the linear trend of the model is captured, the residual should basically be only noise, right? So here in the residual versus fitted values plot, if we see any pattern such as a curve or a wave or a cluster, then it will tell us that the linear model that we fitted is not appropriate for our data. And in another word, that means that the nonlinear relationship between x and y was not explained by our model, and that's why that was left out in our residuals. So in this example, in my R window here, we can see that the residue, the values, these points are randomly scattered around this dashed line. That means the linearity assumption is satisfied. So the second assumption in the line acronym is I for independence. And according to the independence assumption, at each value of x, the values of y are independent of one another. So among these 4 different plots, they do not check the independence as assumption, and that can be done separately by other measures such as checking autocorrelation that we will not do here. And the third assumption is normality, N for normality. And according to the normality assumption, the distribution of y at each values of x is normal. And this is same as saying that, or assuming that the errors are normally distributed. So to check the normality assumption, we can look at the normal quantile plot here, the second plot, normal, also called normal QQ plot. And in this plot, if the standardized residuals align with the straight dashed line here, you can see the diagonal dashed line, then we can be confident that the normality assumption is satisfied. And the idea here is, if the residuals are normal, then their quantile would match the theoretical quantile of the normal distribution. And so if they match, all the data points will be along this diagonal line. So in this example plot here in R, most of the points, we see that most of the points are along this straight line, near this straight line, and I would not expect a very perfect straight line, all of the points falling on the same line. I would not expect that. But in totality, it should sort of fall around that line, along that line. And here in this plot, I see some observations like 22 and 22 is little off. Other than that, it looks good to me. And if you see any points that are like very off, like coming very down or having very high value of residuals, then we can rerun the model to perform a sensitivity analysis with and without these observations to see how much your value changes, how much your results changes with or without these values. And based on that, you can decide how to deal with that observation. And in my work, I try as much as possible not to exclude the data points until and unless they're highly influencing the results. And we will talk about that in the residual and versus leverage plot later. Now let's look into so for the purpose of our data here, it's the normal QQ plot sort of shows that the normality assumption holds. The fourth assumption is homoskedasticity, also called equivariance, E for equivariance. And according to this assumption, the variance of y at each value of x are equal. And this is same as assuming that the error variance does not depend on the value of x. So in the diagnostic plot, we can check this assumption using the scale location plot, which shows the spread of residual across the range of values of predictors, the fitted values. And in this plot also, if we see any randomly distributed residuals, the equivariance assumption will hold. But if the distribution is showing any patterns, like we discussed in the first plot, then there would be heteroskedasticity, not the homoskedasticity. And in the diagnostic plots figure, here in this figure, we do not see that sort of pattern here. So I would take it as the homoskedasticity assumption being satisfied. And in the diagnostic, in the fourth figure here, in the residual versus leverage plot, this plot is very useful because it can help us identify the observations that are extreme on y value. They are also called outliers, and these are located far above or far below this zero residual line. It could be far above here or far below here. They are the outliers. Or there could be other data points called as high leverage points, and they are extreme on x values. So this type of data points are located far right, on the far right side, because they're extreme on our predictor variable. Or there may be the influential observations that have both high leverage and high residuals. And these types of points are far right and far above and below. They are on the far right, and either on the far above, far right above, or far right below. And the influential observations are usually detected by their high Cook's distance value. Here you can see in this figure. And if the Cook's distance value is greater than 0.5 or greater than 0.5 to 1, or if it's more than 4 by n, 4 divided by total number of observations, then also we can say that they are the influential observations. And if we see the outliers in our plot, one technique is to deal with them is transforming the outcome variable or checking the correctness of our data entry. That can help. And if we see any high leverage point, we might want to check our data if they are correctly collected or correctly entered. And for the influential points, doing like I mentioned earlier, doing sensitivity analysis to check the difference in result when including them versus not including them can be helpful. And other techniques could be variable transformation, for example log transformation, or using any alternate regression approach could be done. So in this figure here, in my R window, in the residual versus leverage plot, we do not see that sort of a high data points with high residuals and high leverage or a high Cook's distance. So we can say that the data looks good to us, and we can use this model for our data, and we can use the results from there. So this way we can check the diagnostic plots and analyze if we can use the results from running your model, or take any corrective action before rerunning the model, or think about any alternate model. I hope you found this video useful. Thank you for watching.